Good afternoon, everyone. My name is Ross, and this is Victor. He's going to be helping me with this screencast. Our team name is Marv. It's because it's the first initial of all our names, because we're not creative at all. Our project is an item creation database. It's basically the element of randomization within a game whenever it creates an item. And Victor will be explaining what this project is about.
All right. What is this project? Before I even get into that, this project really takes a look into the world of game developers. It also takes a look at databases and how they interact with video games. So here's some major things that databases do in video games, which are storing character profiles, saves, storyline of a game, created characters, monsters, etc. So how are items kept track of as game develops over time, you may ask? Well, it's not that complicated. Items exist in two forms when it comes to a game. There's static items and there's dynamic items. So static items, items that are pre-existent in the game. So they're items that already exist and have like unique stats to them. Dynamic items, however, are items that, as they fall out of a monster or whenever a character buys them off a shop, are generated on the spot. So literally as the game progresses. For example, in our game, what we'd have is a base name, a prefix, and a suffix per item that is dynamic. So what happens is when an item drops, it looks at three tables, a base, the prefix, and a suffix, grabs one element of each table, puts it together to form one element, and creates that new item as a whole.
Alright, so it's probably a little difficult to imagine, so here are some examples of what a dynamic item would look like with the prefix, name, and suffix tables being used. So a sailing is grabbed from a prefix table, and so a prefix table might look something like this: angry, apologetic, apprentices, blessed, chromatic. These are all prefixes that could be attached to an item. So this one grabbed a sailing. Conquest sword would be a name. There would be a database filled with different names for items, like there could be conquest swords, battle axes, things like that. Then of discord would be from a suffix. So the suffix is grabbed from a suffix type of a table, where it could be like of darkness, of light, of Zeus, of the archangel, etc. And all these prefixes and suffixes are put together on the item to create an item, and that's how dynamic items are created during a game. Whereas a static item, if you were to buy a static item, it's predetermined. You can see this name is not something that's created using a prefix, name, and suffix. It's just the executioner. And all of its affixes are predetermined. As you can see, it's not randomized. So taking a look at the database, you can see all our prefixes here. This is actually in alphabetical order, so you can't see all the prefixes or suffixes that we have. There's quite a long list, so you can create quite a few different unique items from that. And these are some examples of items that were created within a database, like vicious sword of the bear, a prefix, name, and a suffix. Shiny tall shield of the titan, prefix, name, suffix, etc.
Alright, so how is this all implemented, you may ask? Well, our group decided to create four implementations of this game. And starting the first implementation was an entirely Java-based implementation. What that means is the prefix, the base name, root name, and the suffix of an item are all contained within three separate text files. What the program does is it reads each of these separate text files, grabs a name from each of these separate files, and then assorts them together to create one item. Then this new item is written to a new file, and that is where it's held. So for our second implementation, what we do is that now we're using a database. That's when the fun starts. We're using a database with SQL statements. However, there's no indexing involved whatsoever. It's entirely made out of search queries, and so there's still some file usage in there. So what happens, what I mean by this is that the prefix, suffix, and name tables are all stored as files in Java, but all newly created items are then stored in the database. So it's almost as a hybrid. The implementation 3 is embedded SQL with full database usage along with indexing. So now it's switched to a complete database storage system. And there's additional indexing to go along with that. And the indexes are applied for each attribute, each separate attribute. Now for the fourth implementation, we actually regressed a bit, where we looked at the current implementation and said, hey, what if we take out indexing? So we still have a full database usage, where it relies completely on storage on the database, but there's no indexing involved whatsoever. It's just a Java program and a database on their own, and they work together to form, to run the game.
Alright, so the reason we had all those different implementations is so that when we tested them, we could see how quickly different implementations run as compared to other ones. We used three tests. The first test was one where it just was creating 100 items. Every time it creates an item, it calls all the different tables as we've discussed earlier, and then it adds that item to a new table called the items table. So we did that for 100 items, and we timed it using system.nanotime, which we ended up converting to milliseconds since the numbers were so large. And if we take a look at the data, we can see that for 100 items, using only the file system, it took about 10 milliseconds, 10 to 12 milliseconds, and that's really not that long, but we realized that with a larger game implementation, if there were, for games like Diablo 3, which are really popular, and there's at any point in time tens of thousands of people playing the game, all who are presumably killing monsters and making items drop, that there would be tens of thousands of queries every minute to the database to create a new item, which would make the time that it takes in milliseconds pretty significant. So when we took a look at the other implementations using a database, we saw a pretty significant decrease. It was up to 20% in some cases, and in our third case where we used indexing for items and for prefixes and suffixes, it was significantly shorter at about 40%. In our test B, we used 500,000 tuples to query a search. So basically we were trying to find specific items, say a character is equipping a certain item from their inventory. We need to be able to search for that item, change its status of being in the inventory to being equipped on a character. And we figured that any one character would probably never have more than 500,000 items in their inventory, but we just decided to use 500,000 so that it could be a more significant number to calculate. And we did several tests to find the average using 500,000 tuples. So as you can see from the table, the Java-only implementation took nearly 20 seconds. It was about 19 seconds, and the database that used or the implementation that used the database as well as the Java files was 17% faster. Once we had indexing, it became 30% faster, and then when we took out indexing but made it entirely database implemented, it actually ended up being about the same speed as our database and file implementation, which was kind of surprising for us. And then for our third test, test C, we decided to see how long it would take to print all the tuples from the items table. So basically it was just going through the database, finding each item and sending the data back to our Java file, or to our Java implementation to print out all 500,000 tuples. I'd say most of the processing time was based more on like computer speed and the Java program itself, since the Java was the one printing everything, but it did still have to call the database for every item that it printed. And that actually ended up taking a little bit longer than searching for an item, which I guess makes sense since we were only searching for one item. It was about twice as long at between 30 and 35 seconds for our Java-only implementation. And then the trend followed where it was approximately 20% faster for our database implementation with Java. Indexing made it slightly faster, but it didn't really make much of a difference. In fact, we're not even sure if that was really much of a difference, or it's just because, or if the test cases would have eventually averaged out, because indexing um, doesn't really help when we're taking all the data anyway. And our database only implementation showed about the same sort of data trend.
So what did we learn from this? Well, above all, we did learn, well, more or less, we already kind of knew this, that databases are integral for storage of not only video games, but for any large aspect of storage processing in any application. We also learned that when it comes to storage of information and data, including text files, when it includes text files, it's fairly inefficient, it's bulky and time consuming. Therefore, the use of databases as a form of storage proves to be an effective solution in maintaining and managing vast amounts of data. As like our items in our make believe game, it dealt with many different items and it had to create items using many different categories, etc. The use of index worked best to eliminate the cost of searching based on only specific attributes rather than having to go through the entire table. However, when looking at every possible tuple, there seems to be no difference in performance. Like we said before, some of our items had specifications on which prefix and suffix they could use to combine to form an item. However, other items didn't have this specification and any of the prefix and suffixes could be used. In these instances, indexing did not help because all the tuples would have to look through anyway. So it doesn't matter where you start looking through it. Also, switching implementation to entirely embedded SQL code, so the one that did not deal with files whatsoever, um, did improve the performance, but indexing in particular did not significantly improve it because it was only quicker by a few milliseconds compared to a standard SQL implementation, but was easier to manage through a SQL, for a database SQL. All right, thank you for watching.
Thanks, everyone.